Welcome back. Thanks for joining for the second class. Last time we have discussed about the how to calculate the COG for the simple beam and for the two-dimensional object. Now we will talk about the three-dimensional wake and COG. For this three-dimensional, there is no it's not really complicated as we've seen in here. The formula we use still the same as previously. It's like if you still remember, if you want to find the COG on x-axis, then we will use we will refer to the x coordinate of each items. So let's say P1 times x1 plus P2 times x2, and it depends on how many items you have in the system, and then divided by the total load. Now we have additional axis here. It is the z axis. To find the z coordinate, the COG for z coordinate, then it will be the same formula we will be used, but the difference is only the reference of the coordinate we have here. So for the COG z, we will use P1 times z1 plus P2 times z2, etc., etc., divided by the total load. If it's additional, it's additional load. But if it's there is an install item, that will be minus. So yeah, the formula will be that will be used is still the same. So the difference, the reference of the coordinate will be used in the calculation. So for example, we have three items. Item one, the color blue. Item two is the yellow, and item three is the green here. And we will lift it together with 4 lifting points for the crane 1 here, crane 2 here, 3, and 4. So to to get the lifting point reaction, we need to find the combined COG of this system. To find this combined COG, then we need to calculate it using the formula that we have here. So for item 1, the weight is 600 kilonewton. For item 2, the weight is 300, and the item 3 is 500. And the COG is, as we can see in the table, there is X, Y, and Z. And we need to calculate the weight COG and lift point reaction at each cranes. So now we want first we calculate the total weight. We just put it. We can simply calculate it P1 plus P2 plus P3. We get the total weight is 1400 kilonewton. For the COGX, we will use the formula P1 times X1, P2 plus P2 times X2 plus P3 times X3, and divided by the total weight, and we get the COGX is 12.1 meters. COGY, same formula, but the axis for the our reference is using the y-axis. So P1 times y1 plus P2 times y2 plus P3 times y3, and then divided by the total weight, and we got the YCOG is 4.14 meters. For the COG Z, same, we will use the same formula, but our reference for the axis is coordinate Z. for each item. So P1 times Z1 plus P2 times Z2 plus P3 times Z3, and then divide it by the total weight and get the COG Z is 2.89 meters. That's for the combined COG and the total weight. Now, to calculate the lift point reaction, we only need the COGX and COGY. So we don't use the COGZ to calculate the lifting point reaction. The COGZ is usually only for the stability studies. So there's no need to use the COGZ for the lifting point reaction. So for this, from this we can calculate the lifting point reaction same as previously. So we have the COG X is 12.1 as we have calculated 12.1. COGY is 4.14 meters, and the coordinate are based on our origin point here. This is X and this is Y, and this is Z. Now we calculate the lifting point reaction. We have the COG here, 12.1 meters X and 4.14 meters Y, and the distance between lifting point is 20 meters X and 10 meters Y. So same process as previous. We just we need to distribute the load from the COG to each pair of sides. We can distribute it to left and right, or up and down here. So for this case, I will distribute it first to this to left and right. So if we look at this side, then it will be like this. So the P total, the weight of the system is 1400 kilonewtons, and it will be at the 12.1 meters from crane 1 and plus crane 4, this one. Crane 1 and 4 will be at the left side, and crane 2 and 3 will be at the right side here. So it will be, because the total distance is 20 meters, so the load will be 7.9 meters from the crane 2, 3. To calculate the crane 1, 4, crane 1, 4 is a combined reaction from crane 1 and crane 4. So crane 1, 4 times 20 meters. 20 meters is a distance from this to this. So crane 1, 4 times 20 meters minus P total. P total is the total weight times 7.9 meters. 7.9 meters is. And then we got crane 1, 4 is 553 kilonewtons. And then we continue with the crane 2, 3. Crane 2, 3, then we will use the total moment at crane 1, 4 equals 0. So the formula will be crane 2, 3 times 20 meters, the distance to crane 1, 4 here, minus P total times 12.1 meters equals 0. And then for the crane 2, 3, we got 847 kilonewton, like that. And then we continue to distribute each combined reaction to each lifting point. So first we distribute the crane 1, 4 first. So for the crane 1, 4, for the first step, we distribute this to left and right, and it will be at here. And then for the crane 1, 4, we will distribute looking at this side, then we will be like this. This is crane 1, and this is crane 4. And the load combined reaction 1/4, it will be 4.14 from crane 1, and the rest 5.86 from the crane 4, like that. Now we can continue with the crane 1. So we use total moment at the crane 4 equals 0. So what is the moment at this point? Then it will be crane 1 times 10 meters minus crane 1/4 times 5.86 equals 0. So we got for the crane 1, it's 324.1 kilonewton. And then for the crane 4, then we will use the total moment at crane 1 equals 0. What is the moment at this point? There are crane 4 times 10 meters minus crane 1/4 times 4.14 meters. And then we get the crane 4 is 228.9 kilonewton. And then will be the same with the crane 2/3. Crane 2/3, we got previously we got 847 kilonewton. To get the crane 2, then we will use total moment at crane 3 equals 0. What is the moment? What are the moment at the crane 3? They are crane 2 times 10 meters minus crane 2 3 times 5.86 meters. Then we got the crane 2 is 496.3 kilonewton. For the crane 3 also we will use the same methodology. So for the crane 3 we use total moment at crane 2 equals 0. So we got the crane 3 is 350.7 kilonewton. Now we do the equilibrium check. So the total load from upward will be should be same as the total force downward. Crane 1 plus crane 2 plus crane 3 plus crane 4 should be equal with the P total. So in here we get the total load is 0, so it means that we are in the equilibrium state, or the reaction is already correct. So it will be the same as the two-dimensional load distribution. While the COGZ, we only use that for stability studies, like that. Now the case 2 is we have a jacket structure here, and the origin point it's here. So the x-axis is here, y-axis here, and z-axis here. So if you look at this table, this is a real project that I have recently. So if you look at this table, you will see that I calculated using the same methodology as we have studied here tonight. I check one by one, piece by piece, and one item per for each items. I check the weight and the COG. The COG will be refers to the origin point we have here. So I calculate manually, and then I get the total COG here. So I use the same methodology as we have studied here, and this jacket is already lifted with the design, and it's on. There is a minor tilting. It's not a big deal, but I could say it's a successful lifting with this, and I designed the rigging based on this COG. So what I'm trying to say here is it's that it doesn't matter if you just calculate it manually, but it will showing the same result with the if you calculate it with the software. So this jacket is going to be transported by using SBMT. For the SBMT, we will use 4 groups hydraulic with 100 kilonewton scaffolding installed at top elevation. So this jacket will be transport with scaffolding at at the top. So calculate the weight, COG, and reaction of each hydraulic groups. For the COG, we will use the same methodology as previously we have calculated. We will use the same formula. So first we calculate the total weight of structure is 3,516.5 kilonewton here. That's based on this calculation. So it is in mass, this one. Then we need to calculate the weight. Then we will multiply it with the gravity 9.81 meter per second squares, and then we get the weight of structure is 3,516.5 kilonewton. And then for the weight scaffolding, as mentioned before, it's 100 kilonewtons. Then the total weight will be 3,616.51 kilonewton. Now we combine the COG. The weight is 3,516.5, and the scaffolding is 100 kilonewton, and the COG X, Y, and Z as on the table. So this COG should be reversed to the or measure to the origin point. So to calculate the COGX, we just use the formula P1 times X1 plus P2 times X2 divided by the total weight. The weight of structure here times the COG of the structure 10.008 meters plus 100 kilonewtons times 10 meters the COGX of the scaffolding divided by the total weight, and then we get the COGX is 10.008 meters. For the COGY, we use the same P1 times Y1 plus P2 times Y2 divided by the total weight. So we get the COGY is 9.996 meters. And also for the COGZ, P1 times Z1 plus P2 times Z2 divided by the total weight, we got 20.9 meters. So if we plot it into the drawings, it will be the combined COG will be here, 20.9 from our origin point. It will be at the bottom of the structure. Now we want to try to calculate the hydraulic point reaction. Just a little bit about this how this hydraulic SPMT groups works. So the hydraulic groups work. The center of the hydraulic groups is the center of the center of the reaction for each group. So the load distributed from the COG to the each center of hydraulic group. That's how the load to be distributed. And the center of hydraulic group will be at the center. So for example, we have 1, 2, 3, 4, 5, 6 axles lines here for one hydraulic group. Then each one axle means this one, right? One axle consists of two bogies. So if we look at the section view, it will be like this, right? This is the bogies. So this all mean we saying as one axle line. So it will be this. This is one axle line. So in this SPMT we have 6 axle lines, and each axle lines consists of 2 axles. So this is the axles, and each axles consists of 2 bogies. This is the bogies. So to to make it as a one hydraulic group, then we will connect all the axles. So if we have these axles in the on the SPMT, so 1 2 3 4 5 6, 1 2 3 4 5 6, this is the axles. Then we need to connect all these axles like this, and the center of this hydraulic group, this is the point where the load to be distributed from the COG. So because this so for this is for the 4 groups, yeah. Now if we if we, let's say we make it as 3 groups, then it will be like this. The center of these groups will be, let's say it will be here. Then the load will be distributed from the COG to this center of group. And the stability, the tilting line, the stability line will be like this. And this COG will be distributed to this center of group. From the center of the group, it will be distributed equally to all the axles. So that's the unique of the SPMT, because it can distribute the load equally for all axles. So yeah, unlike the conventional trailers, it will depends on the springs, how much the stiffness of the springs, and it will impact to how much loads will be distributed to the axles. So yeah, that's how a little bit about the SPMT. So for this case, we have 4 groups, and the first thing we trying to do is to distribute this load to 4 center of hydraulic group here. So now it will be the same as we calculate the lifting point reaction. We only need the X and Y coordinate, and the Z coordinate, we will use that for the stability during transportation or heavy lifting. Now to calculate the reaction of each groups, then it will be the same as the lifting point reaction. So when we first we will distribute, for this case I will distribute it first to this side and this side, right? So if we look at this side, then The group 1 and 4 will be at the left, and the group 2, 3 will be at the right, and the COG will be the center of our load in the system, the P total. And the distance will be 10.8, 10.008 and 9.992. And the total will be 20 meters, like this. We follow this, the COGX. So we calculate the group 1-4. Group 1-4, we got that means we will use group 2, total moment at group 2-3 equals 0. So what's the moment at group 2-3? There are group 1-4 reaction times 20 meters minus P total times 9.992 meters, the distance to group 2-3. So we got group 1-4 is 1,806.8 kilonewton. So, and for the group 2-3, we will use total moment at group 1-4 equals 0. What are the moment at the group 1-4? There are group 2-3 times 20 meters, group 2-3 times 20 meters, minus P total times 10.008 meters. So we get group 2-3 is 1,809.7 kilonewton. So, and then we distribute from the combined reaction. For group 1-4, we will distribute to the group 1 and group 4. We get we will use the same methodology. So we got group 1 is 903.8 kilonewton and group 4 903.0 kilonewton. And it will be the same as group 2-3. We will distribute to the group 2 and to group 3. So we got group 2 905.2 kilonewton and group 3 we got 904.5 kilonewton. Once we get the reaction from each groups, then to calculate the ground bearing pressure of each axles or bogies or tires, so now we could distribute this. We just simply just divide it by how many axles you have on the group. For example, for this case, we have a 6 times 2, so we have 12 axles, right? If the reactions for group 3 is 905, then the axles load will be 905 divided by 12 axles. So that's the axle load. To calculate the ground bearing pressure, it will be a different. There are another methodology for that. There is a shadow area methodology. I think it will be more detailed in the fundamental transportation class. So yeah, that's for the grouping calculation, reaction calculation. Now the same cases we have here. We have jacket structure. The mass is 358.46 metric ton, and the COG is here. Now this jacket will be lifted by using a single crane and determine hook position if the minimum requirement of rigging angle is 60 degrees to horizontal. That's the minimum requirement. So it's okay if it's more than 60 degrees. If the actual hook point is located at 50 millimeters toward X plus and 30 millimeters toward Y axis from the original design, calculate the tilting angle that could be happen during lifting. So that's how we use the COGZ in the calculation. So the COGZ, we can use that information to calculate how to estimate how much the tilting angle could be happen if the hook will be not in line with the COG. So first, determine hook position. Ideally, hook to be located in line with the COG position. It will be like this. So if the COG is 10.008 meters, then it will be in line. The hook will be in line with the COG. That's the ideal uh, for the hook position. Now, to calculate the rigging length, then we need to know the horizontal length. The horizontal length is this length, the distance between the uh, lifting point to the COG. This, like that. So we can find that by using the Pythagoras. So it will be L for this, yeah. Square root 10.008 square times this 9.996 square, like that. That's for the rigging one. This. So for the rigging one, we get the LH, the horizontal length. LH is 14.14 meters. Rigging 2, we get 14.13. Rigging 3, we get 14.14. And then the rigging 4 is 14.15. Now, based on this length, we can calculate the height of the rigging. Is but it's still based on the 60 degrees requirement. So for the rigging one, we got 24.49, rigging 2, rigging 3, and rigging 4. But if we try to connect all this rigging, it will not meet in one point. Like for example, rigging 1 and rigging 2, it will have a little gap. It's about 20 mm. So like this. This is rigging 1, and this is rigging 2. There is a little gap here, and it will doesn't meet with the single point. So we need to adjust one of this rigging. To adjust this rigging, we should reverse to the highest highest rigging. So in this case, there is 24.51. So this is our reference of height. So we need to redesign the other rigging, because if we use the smallest height as the reference, then we need the other rigging we will redesign, and we will meet that the sling angle will be uh less than 60 degrees. So that's why we need to use the highest rigging. So that's for the rigging design. And now the next question is if the hook position is not exactly in line with the COG, so it will be 50 millimeters to the x-axis and 30 millimeters to the y-axis. Then what could be happen then? This COG, this is the initial COG. when we're doing the lifting, the initial COG will be rotating to the final COG where it's in line with the hook. That's what will be happen. So to calculate how many how much the tilting angle that we have here is, then we could simply just using the trigonometric here. So the distance COG to the hook, h this is the distance of the COG. Sorry, the distance COG to the hook is this. So it will be from the lifting point is 16.6, and then the rigging high is at 24.51. So we get the distance COG to the hook is 41.11 meters, like that. Then the delta X, as mentioned earlier, that it will be 50 millimeters or equals to 0.05 meters. Then the tilting angle toward the X direction is we will use the tangent arcus tangent delta divided by distance COG to the hook. So the delta is at 0.05 and divided by 41.11 meters. So we get the tilting angle to the on x-axis will be 0.069 degree, and we will use the same methodology for the y. The delta is 30 millimeters, and then we get the we will use the arcus tangent delta divided by the distance COG to the hook, and we get the tilting angle toward y axis is 0. 0.042 degree, like that. So this methodology also we can use as a reverse engineering to estimate the COG location when we doing weighing by lifting. If you have a familiar similar experience with this, so this is how we calculate the COG for the weighing lifting. So for this up until now, is any question from your side?
Yes, any question from your side? Paul, Mohammed, or Joseph, do you have any question?
From my side, there's no question. I think it follows a simple progression. All I can say that we need to do is go back again and go through it again and again. It follows a simple sequence, the
Correct.
calculation. Yeah,
Yes,
that
correct.
we need to go through it over and over again so that we'll be able to, where possible, we can impute different values to test the whole thing. I think it's okay by me.
Okay.
Yes, yes. It's okay also till now, but I
Mohammed?
have to, yes.
Yeah,
It's okay
so
to me till now, but I have to go back again and again also because
yeah.
it's a little difficult to me.
Yeah, it's okay. If you need something to guide you, you can just directly message me. So yeah, I think that's all for the COG weight and COG calculation on also the load distribution. If you have no question, then we will continue with the other topics. It's a little bit out of topic, but still related with the yes, Joseph.
Yeah, Nelson, on the riggings, the sizes, the length. Can you go back to that slide, please?
Yeah, sure.
Riggings 1, 2, 3, 4.
Sorry. Rigging. Yeah, this one.
Yeah, here.
Yeah.
Step down again first. Next down. Yeah, over here. Okay.
Yeah.
So in our calculation, we used the longest one, rigging 4,
The highest one. Yeah.
the highest. Yeah,
Yeah.
the highest length. If we go by, say, the average of it, does it still work?
The average,
Of rigging 1 to 4.
the problem, yeah, but the rigging for will be the rigging angle will be reduced, calculate based on the 60 degrees angle,
Maximum,
correct? That minimum.
minimum.
And if we reduce the 24.51, then we get the angle will be reduced to be less than 60 degrees, and it doesn't meet the requirement anymore.
Okay.
Yeah, so that's why we use the highest as a minimum.
Okay, great.
Yeah,
Thank you.
no problem. If any question? If there is no question, then we will continue with the other topics. It's a little bit out of topic, but still related with the weight and COG calculation. So in the heavy lifting and transportation, we know in the project especially, we know there are several types of weight that we can use in the calculation. There are net weight, gross weight, and the NTE. Now, what is the difference of these three things? Is for the net weight is the weight of an item without allowance. So this allowance is cover the modification, if any, from the initial design. So there will be, so if we're familiar with the stages of of one project, there are design stage, construction stage, and installation stage, and these three stages will give there will be a lot of modification that could be happen during these three stages. That's we set in this as a allowance. So the net weight is the weight of an item without the allowance. So it still not cover the modification. And it is the actual weight obtained from manual calculation or by using software. For the gross weight is the weight of an item including allowance. The formula will be net weight times weight contingency factor. And this is the weight used in the lifting and transportation analysis. For the item number 3, weight number 3 is NTE. This is the maximum allowance weight limit. So we will see in the here. This is what I got from ISO 19901. So if we look at this picture, the net weight is on this the red color, and the gross will be the blue here. As we can see here, the net weight it will be climbing up, depends on what stages we are doing the project. So if we use the net weight for calculating the heavy lift, to design the heavy lifting, then we should see what's our reference in the drawing. If it's the drawings that we refers to based on the design drawing, then it will be on this, let's say it will be at this stage, yeah. Then we need to estimate, we need to cover this wake allowance to get our design into refer to the gross weight. So what I'm trying to say here, we need to see what stages, we should understand what drawing we use in our design. If it's in the design, then we should reverse, we should multiply the weight in the drawings with some factors that maybe we can reverse to some codes to get the gross weight. I think the NP or ISO is also mentioned to how to get the gross weight. So yeah, and the NTE weight will be, the NTE weight is here. Now, if we use the NTE weight, yeah, it will be safe, but it's no longer efficient for our design because it's pretty excessive. So yeah, I think for our design in heavy lifting just refers to the gross weight. This is for the example of the weight contingency factor I took from total specification. As we can see, there is 3 stages here during the project. For the one project, there are basic engineering, detail engineering, and construction. Now, even if we have doing the weighing for the structure, we need to put the contingency factor just to consider if any modification that will be done after the weighing. So the weight it means the net weight after the weighing. Then we multiply with the contingency factor to get the gross weight. That's for the gross weight, and this is the guidance criteria for weight control class selection. I got this from ISO. There are 3 classes that we have for to classify the structure that we have. So class A is a new concept type, weight sensitivity high, COG sensitivity high. It's like let's say it's a new tops, we can say that like new topside construction, for example. And then the class B, concept type partly known weight sensitivity. For the class B, let's say it's a one part of the topside. So for example, we have one topside with three different 3 levels. Then each levels we can classify it as a class B, while the whole topsides will be classified as a class A. And for the class C, we can say, for example, is one part of the what's one of the equipment in the one level. So the smaller part of the top side will be the smaller classified. It will be smaller classified like that. For the class C, you don't need to do the weighing, but for the class A, you need to do the weighing, and it's because the weight sensitivity high and the COG sensitivity high. Now, beside the gross weight, we need to consider also of the COG, because there is maybe modification during the stages of the project. So to calculate to consider the modification, we can use this. There are two methodologies that we can use. First is a COG envelope. It is one of the methods used to test the design for uncertainty in the COG, and generally used for structure item class A as per the ISO that I showed you before. And for example, we could reverse the total specification here. The extremes of COG envelope center around the calculated COG, which corresponds to a rectangle whose sides are, let's see this, for example, like this, we have a top side here, right? Let's say it's size 20 meters times 10 meters. And then the COG is here. Let's say it's 15 meters. Now, if we use the COG envelope for our design, then it will be 10% of the overall width, and as per the total, it will be 10% of the overall width and length. So it will be the COG envelope will be, it will be a box where the COG, the original COG, will be at the center of the box. So the size of this box will be 10% of the overall width, 10% of 20, then it will be 2 meters, and this will be 1 meters. And we will analyze this our design. We will calculate our design based on the critical load case. Now we have 5 load case that should be considered in our design. First is the original COG, and the second is the COG if based on the critical point of the COG envelope, it will be here, 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 here. So we will design we will calculate our design based on 5 cases. One is the original COG, and then we continue with this additional COG based on the COG envelope. And then we find what is the critical case, and we will design based on this the critical that we found that. So yeah, that's for the COG envelope. Any question about this COG envelope?
Any question? Everyone, Muhammad, maybe do you have any question regarding COG envelope?
This methodology we usually use for top side lifting that potentially have a lot of modification like that. So this COG envelope will control also for the design to put where the modification should be placed, so that the COG will be not moving out from the envelope. like that. And also for the heavy lifting design, we will use that to calculate the which cases the more critical that can be happen in our project, like that.
Yeah, Muhammad, you unmute now. Do you have any question related with COG envelope? COG envelope we can use for topside lifting operation. So if you have any question, or maybe this is first time for you to listen about COG envelope, feel free to ask to Nelson.
Yes, actually, this is the first time to hear about COG envelope, but it's okay to me till now. Also, I will go back again and check because I know there is COG factors, for example, in ad hoc limbs, COG shifted factors, but this first time regarding to COG envelope. But it's okay. It's not difficult like before.
Good job, right, Muhammad? Yeah. So
Yeah.
if you don't have any question, you can continue, Nelson.
Yeah. So the next one is about the COG factor. Beside the COG envelope, we can also use a COG factor to accommodate the uncertainty of the COG. So COG factor is another method using a factor as a substitute for the COG envelope, generally used for structure or item class B and C as per ISO. And if we refers to the total specification, it is mentioned that COG factors is one that we can use we can apply is a 1.05, but it's not limited. You can use any reference. I think the NV also mentioned about the COG factor. Maybe you can refers to the NV or another reference like that. So yeah, I think that's all for this class. Maybe you have a question about the load weight distribution, like that.
Also from our previous class, if you have any question, you can ask.
Yeah.
Maybe Joseph, you can ask. Go ahead, Joseph, you have a question?
Yes. Yes. Thank you very much, gentlemen. I just want to ask, while calculating the load distribution and COG, what if it's a live load?
Live load is it's usually used for a structural analysis. Yeah, it's like people people on the structure, like that. That's a live load. While the dead load is the structure itself. But for the heavy lifting, we never use the live load as in our calculation. It's always using the dead load.
I think live load is lifting versions or like
Sorry?
that.
No,
Sorry?
live load is what I said.
It's a person
The
in
structure is built on structure. For example, people walking. So basically, live load we use for calculate the structure analysis for height building.
no, it's also there is also for offshore structure.
For
It's a
offshore.
general,
Like
yeah,
people,
general structure,
people,
but
people
yeah,
walking is like this, yeah.
yeah.
People walking on. Also, for example, bridge, vehicle. It can be live
No,
load.
it's a vehicle load.
Vehicle load. Okay, so
Yeah,
it's vehicle. It's kind. So this is part of live load.
yeah.
Okay, I just want to ask you another one just in relation to it. For example, let's say that we have a tank a tank that is filled with fluid, maybe diesel or hydraulic or oil, anything's fluid, for example, and there is no chance of draining it, of emptying the tank before
Yeah.
lifting.
Yeah.
And there will be a considerable movement of the fluid inside the container. How do we try to make sure that we are rigging it up and our calculations as per COG, it's okay?
Liquid, is it in the pipe, or because there is dynamic, let's say if there is a space of like this, yeah, if there is a space between the liquid in the tank, then we should calculate it. It's a advanced calculation to calculate if there is a dynamic, uh if there is a dynamic in the tank. But if we COG, based on the COG, we could easily, if it's a static, then we could easily say that the liquid, we could calculate based on the previously formula. We have
Mm,
volume times density.
yes.
Yeah. So if the volume, we could calculate the volume of this the liquid, and then times the density. That's the mass, and then the weight itself will be mass time the gravity. But that's the static calculation. If dynamic, then it will be a different case for this. I think that's I hope that could answer you, Joseph.
All right. Thank you very much. Thank
No
you.
problem.
Jonathan, I've seen some lifting operations, and when they were trying to make the lift plan and design and calculations and stuffs,
Mm-hmm.
it's like a tank. Okay, tank, right?
Mm-hmm. Mm-hmm.
TANK, tank.
Yeah.
Yeah, and this tank contains some fluid inside, and there was no option to drain it,
Yeah.
to empty it prior to lifting.
Yeah.
So, for example, if the tank is not completely filled up, there will be a movement, internal movement, a dynamic movement of the fluid
Mm.
inside the
Sloshing.
container. Yeah. And it will keep changing. The COG will keep changing as it's moving, as the
Yeah.
fluid is moving.
Yeah. Correct.
Yeah, that's where my question was
Yes.
focused on.
Yes. That will be on dynamic analysis for that, and
Okay.
that's will having some advanced calculation
Um,
to
can I add one thing here to
yeah.
in relation to Joseph's questions here?
Yeah.
Normally in offshore, if we are doing any lifting,
Mm-hmm.
even it's partially empty or partially full, as long as you have four lifting points, it doesn't matter. The COG, it won't matter, yeah. Either
Mm.
partially filled or partially full, as long as you have four legs, or I mean four lifting points. It will balance, the lifting, either dynamic or static operations of lifting the tank.
Yeah. The pro
You agree with me, Nelson?
the problem is if it's there is a dynamic on the liquid, it will change the COG for because the liquid inside the tank will be splashing uh any direction that we cannot predict it. So the splashing of the liquid, we could changing the COG very fast, and probably the it the system cannot catch it, uh, and it will overturn the structure itself. That's why for liquid analysis, it's a little bit complex, but it will require advanced analysis to calculate the CO, to analyze the COG. For static, we can use the simple like this, but for the dynamic, it will be more advanced. It will require a more advanced calculation like that, Joseph. I think you got my point. Do you agree
Yeah.
with me, Edmund?
Yeah. It sometimes it depends also if the tank has a
Correct.
buffers.
Correct.
If there will be buffers, then there will be reduced in the slushing of the liquid. That's what I'm trying to say.
Yes.
It depends on static or dynamic operations. If there will
Yeah,
be
correct.
buffers, then yes. That
Yeah,
it won't
if
matter, yes.
yeah, if the structure weight comparing to the liquid, the structure has more weight than the liquid, then I think that's no problem. But if the liquid, like the tank, has the liquid has more weight than the structure, then we need to analyze the COG based on the dynamic.
Yeah, I also agree with Nelson because when liquid moving unpredictable, it is very difficult. And also, I think that the other concern that we have to think about, um, if we lifted this liquid, for example, this tank to offshore, so there is also dynamic load, yeah, for this. So we can calculate that but this is for advanced calculation because the liquid itself moving and it's very difficult to predict. And as we know that if we lift it load unbalanced, so it will be add more weight to the load. So that's why, like Nelson said, that it's better we not play game with that one. We have to calculate properly to avoid a significant additional load that can be added to the load during transport to offshore. We don't know. For example, if we have to lift this from bars to platform or from bars to TLP like Tencent like platform. So there is dynamic operation. Is not only for static operation. It's kind of like that, I think. This is just like additional information that I can add to our case. And Muhammad, you raise your hand. Do you have any concern or you have any feedback for this?
Yes, I have some information regarding to this. I shared in the chat a screenshot. If you can open it
Yeah.
regarding to the dynamic lifting. There is some companies make in own procedures some factors regarding to like this lifting operation. For example, dynamic amplification factors, this depth factors. He add a factors to the static hook load.
Yeah.
Just like add a factor. Static hook load. This is the net weight multiply the contingency factor and the hook block weight and rigging weight factor. So I share it, Joseph, if you can read it and if it's okay for you, it will be good.
Okay,
So
thank you. Thank you. That's great, Mohammed. Thank you very much for that. Thank you
yeah.
for that.
Yeah. So just for additional here, actually it's out of topic, but I will try to explain here. So the dynamic factor here is a factor that we can use to anticipate if any external factors that could be impact to our design. So if this, so what I'm thinking is these factors cannot be used to anticipate the case that Joseph has right now, because the the one that could be happen here is the fluid is the fluid will be moved, and the COG will be changed very very fast, and this happens based on this dynamic will be impact based on the internal forces, not from the external. So I have experience about this before, to lift a tank with the liquid inside, and it will require uh some additional calculation to estimate where is the potentially COG will be moved when the liquid inside slashing to the another direction. So yeah, but this dynamic factor that Mohammed sent to us, it can be used for if for example, it's a offshore lifting with a vessel, and the vessel is kind like making a motion or movement, and then it will impact to the object that potentially will be moving, and it will cause additional load for the crane or for the rigging. That's the dynamic factor will be used. So it's not for the internal forces, or yeah, internal forces like that. And there is also tilt factor. Tilt factor is if we design a rigging with four lifting points, and there is a difference length within our design and the actual. So that's for that's why we use the tilt factor. Yaw factor is for if we using two hooks or two cranes for the lifting. And the COG factor is, as I explained before, that to anticipate it if there is a contingency on the COG. So yeah, but yeah, that's really helpful, Mohammed. So we know how to use that. So any question?
Yeah,
I think
I think that we have to understand what is the difference between, like Nelson said before, between dynamic load and dynamic factor. This is, I think, the dynamic factor DAF, right?
yeah, dynamic factor is the one we
Yes,
use.
Hmm.
Yeah, that's
I
So
just
we have
read.
to know the difference between dynamic load and dynamic factor. For the fluid itself, correct me if I'm wrong, Nelson, okay? For the fluid, dynamic itself is a part of a dynamic load, I think. But this motion for the bars, wind, list and trim, wave, this is part of a dynamic factor. Is it correct, Nelson?
the difference is internal and external.
Yeah,
That's all.
yeah, it's kind of so. Don't make a confuse with the movement of the fluid. Is not a dynamic factor. Don't get wrong with that, right? It's like we have to make it clear. There is a difference.
I got your point. Yes, yes.
Mm. So
I think that's I hope that yeah, yes, Joseph.
Thank you once again. Still in relation to weight determination and the COG, like if you have a load you want to append or append the load, okay? Is it part of this session, or there is another session where we have that? I mean, another training.
Appending
it will be at the part of this session
capstone.
because we have a capstone for that.
Capstone
Yeah.
for that.
Okay.
So you one step ahead.
You just step
Ah,
ahead, Joseph.
okay.
We have,
And
yeah,
and
we have our
and
capstone project for that one, for appending.
okay, and the brother of appending. For example, you have uh, let's say more than one cranes doing the lifting. Okay.
Mm.
You're lifting the object from the horizontal plane and standing it vertically.
Mhm.
At each movement, there is a change in COG as it's moving from the horizontal, getting inclined, and gradually going to the vertical 90 degree.
Mhm.
That calculation in determining the COG and the other factors for that load, is it still here or is it in the capstone?
So the logic is as long the structure is same, the COG will be the same. That's the logic. Many people said when we doing the appending, the COG will be moved to this way or this way. The COG will be the same. It will be not moved. The one will be changed is, for example, if we have structure like this, the COG is here, and then we rotate it, become like this. The COG will be the same, but the distance to the lifting point will be not the same. For example, this is A, this is B, and then it will be changes. That's why
Yeah.
the that's how the cranes load or the lifting point load will be changes for each decrease of the appending, like
Mm.
that, Joseph.
Yeah, so now at
So
this point, if you look at the result, C is smaller. The distance C now,
mm-hmm.
before it's like A, and the
Yeah,
B changes to D, for example. Okay,
yeah,
from the there
yeah,
to here.
yeah.
You see that the D, the distance is more than C. Then the reaction, the force on each of the lifting points, let's say crane A and B or something, it will
Mm.
be different, right?
Correct.
So one of my questions, or one where I need another clarification, is if you have this load on a horizontal plane and you
Mm-hmm.
want to stand it vertically at 90 degree, at each, as the angles are changing from zero coming up, I mean, zero in relation to the ground, okay? As it keeps changing until it stands 90 degrees, where you have the tail, for example, two cranes,
Mm-hmm.
tail crane and the main crane.
Mm.
Uh, how do we determine the force or the reaction on each crane or on each lifting point as the angles keep tilting towards vertical position until it goes to 90 degrees?
So to get the crane lifting point reaction here, you mean?
Yeah.
So we will refers to the horizontal distance. So, for example, if we now like this, yeah,
Yeah.
let's say it's A and B, and this is the tail crane, and this is the main crane.
Yeah.
Now, to calculate this, we could use this A and B. It will be the same. We could simplify that by using a simple beam like this, where is this is the load, and this is the TC, and this is as the MC, and the distance will be now is as A and B, like that, Joseph. Does it answer your question?
Yeah, it does. But I was having a little doubt of the angles keep changing from the angle from the if you look at the TC, okay,
Mhm, mhm.
uh, on the horizontal plane, for example, it goes to 0. But as MC is going up,
Yes, yes,
the angle
correct.
from between the floor and the object starts
Yeah,
to change to increase.
yes, the MC will be increased and the TC will be going to 0.
Yes, exactly.
Yeah,
And my
and
question is, before TC goes to 0, for example, how do we
uh-huh.
know, for example, when we have the angle there, let's say 30, 45, 60, 80, how do we know the reaction or the force on each of them? Because, when we are doing this lifting, it's like it's a sequence. It's being picked
Yeah,
by the
yeah.
cranes, by both cranes at the same time, depending on the type, and gradually it begins to rotate.
Yeah, that's from this A and B. It will be
Yes,
changes based on the angle, correct?
excellent.
Yeah. So that's how it works to change the crane reaction here. The A and B will be changing based on the for every angles that we are calculate.
Hmm.
You got, maybe maybe you can try with the capstone. I will guarantee that you will understand how once you get the capstone.
Okay, okay, that'll be fine. That'll be fine.
Yeah, yeah. I hope so.
Okay. Because I have dealt with it a couple of times, but I still needed
Yeah.
some more clarity.
Correct,
Because,
correct.
the angle keeps increasing from 0 on the horizontal plane till
Yeah.
90 degrees when the object stands horizontally straight. So
Yep,
in
yep.
between this 0 and before it gets to 90, 100%,
Mm-hmm.
some reactions are happening that the load, TC is having less load, MC is having big load.
Mm-hmm.
Uh, I wanted to know at each angle, how do we know what value, what force will be on TC and what will be on MC as it is changing and the angles are changing?
Yeah, yeah,
I
yeah.
think we can keep it at that capstone.
Yeah, yeah.
Yeah,
Yes, yes.
that's from
Correct.
that's fine.
So let's uh, let's get into the capstone and I will explain a little bit for that. So this is the capstone. This is the template we have here. For the first is a simple beam with the distribution load, and another load is a point load, cantilever from B 2 meters. And we just need to find the reaction and find the COG location based on the load configuration as shown. And the next one is find the combined COG based on the of crane. This calculation is very useful to understand how the crane will be especially for the outriggers will be get spread the load to the ground and to help us to estimate what is the outrigger's load for each foot. So here we have 4 items. Just I'm trying to simplify because actually there are a lot of items that we should consider during the calculate crane COG during the lifting. There are many parts that should be considered, but I will simplify by using 4 items only. There is load, boom, carrier, and counterweight. So the load is here. Let's say the weight is 340 kilonewtons and the coordinate is 1x and 12.5y. And then the boom is this one. The COG is 3.7x and 8.4y. The carrier is here and including the outrigger here, and it will be the weight is a 390 and the coordinates is we can see in the table, and the counterweight is here. The counterweight is 700 kilonewtons and the coordinates here. So we need to find the combined COG. Once we got the combined COG, then we can talk about the outrigger forces and then continue with the ground bearing capacity. But for now, we just need to find the combined COG. And then the number 3 is we have a top side here, and we doing a weighing for by using the compression jack, and we get the result like in the table as seen in the table for SPT1, for example. Here the reaction of the compression jack is a 2606.52 kilonewton, and that's for the others also, SPT2, SPT3, and SPT4. So the SPT stands for the support point. So we put this compression load cells on each SPT, and this is the what we show you. What we can see in the table is the reaction of the compression load cells, and the coordinate of the support point we can find it in the drawing. For SPT1, 0.20, 0 is X and 20 is Y. SPT2 is 0.0 means 0X and 0Y. SPT3, 18.0. So the X is 18 and Y is 0, and also with the SPT4. And the origin point here at SPT2, X to this upward, and Y is left side hand. So we need to find where is the COG location. So that's for number 3, and then the number 4 is like this. Calculate the crane slope during 0 degree, 45, 60, and 90. Is it related to your question, Joseph?
Yes, it does.
Yes, yes. So to calculate this, we need to consider the first thing we need to find the horizontal distance from each lifting points to the COG from each angle. So during 0 degree, the distance will be 16.5 and 20.5, 20.1 meters. And then for the 45 degrees, we need to find that. So it will be rotated 45 degrees. And then we need to consider also this offset 3 meters. So if we calculate it, then it will be like this. This is the COG, and let's say this is the main crane and tail crane. Now we need to find all this thing. A, B, C. Correct? And this is 45 now. Then the B first for the A is 45. Wait. So for this, A will be 45 let's say the offset is E. The E times cos 90 minus A. 90 minus 40. And then we get for this we get 2121.32 millimeters. For B, we will get the 16.5 times cos 45. So we get 16.5 times cos 45. We get 11.7. 11,700. Sorry. It's 11,667 mm. And for C, we get times cosinus 45, we get 14,000. So we get, now to calculate the reaction of TC and MC, we get a new system here, where is we can simplify that by using, this is the COG 150 tons, and this is the TC, and this is the MC, and the distance will be A plus B, and this will be C, correct? Now A plus B is a 2121.32 plus 11,667. This will be 13,788, and this is 14,213. And then we can calculate what is the reaction of TC and MC. That's the reaction during 45 degrees, like that. And for the 60 degrees, we will recalculate what is the distance A, B, and C, and then after that we calculate the reaction based on this ABC dimension. It will have a different reaction, like that. So is it clear for you about this?
Yes, it's clear. Just I want to ask a question. The E, what's the name of that E?
It's
It's
the
not looking here.
this E is a offset from the center of the column or the vessel to the lifting point here. So it will be like this.
Okay.
Yeah, we should consider that, because it will give a different dimension for each angles between TC to the COG.
Okay. That's fine.
Yeah. Let's try and give some input for us to be discussed. Is there any question?
Then if I may ask a follow-up question, okay? I know
Yeah.
by calculation we can get it by calculation. For example,
Correct.
you are designing a lift plan for this. Okay.
Yep.
We are looking at the worst case scenario. At what angle does each the reaction on each point on each crane, what it is per time. We are looking at this degree, this angle. This is the tension or the reaction on A and B. The angle increases or changes. This is the resultant reaction or effect.
So
And
it will depends on where's the COG location from the beginning. If it's close to the tail crane, then the most reaction will be at the for the tail crane, it will be at the 0 degree. Then and the critical for the main crane, it will be during the final degree. It's 90 degrees. Like that.
Okay. That's fine.
Yeah.
That's great.
I hope that could answer your question clearly,
It does.
Joseph.
It really, it does. It does. It does. But one more question I have.
Yeah, no problem. You can ask.
Thank you. If the angles keep changing, for example, if we want to do this kind of to impute different angles, what is the reaction? What is the crane, the load at each? Please, sorry about that, gentlemen.
No problem.
Yeah. Sometimes when you have kids and the mom is not at home. Apologies for that.
It's okay.
All right. For example, now using this diagram, and we want to play with the angles, okay?
Yeah.
Starting from there 0 till in between, half, maybe 0, 20, 30. Without having this drawing, how can we dimension it without having this original drawing, for example, without using maybe CAD, AutoCAD, or any other? How can it help us?
Yeah, you can use the trigonometric for or Pythagoras for the calculation. That's the basic to calculate. Yeah.
Okay.
That's the simplest way.
That's fine. Thank you very much for that.
No problem. Yeah. Any question or if
do you have any question maybe from Paul or from Muhammad? Do you still have any question for this topic?
So if no longer any question, I will return this class to Mrs. Dian.
So thank you so much, everyone. Today we finished our basic lifting engineering, and then we already study about load weight calculation, center of gravity, and also load distribution. I hope that all of you understand very well. So if you wanna continue for this for the next class, you can take rigging design, which is rigging design next month, end of next month. And also, but I think that we don't have a mobile crane stability, mobile crane stability tomorrow. No, next week. So for the next class is mobile crane stability next week, April 29 and 30. And then the last topic for the basic lifting engineering next month, end of next month. I think that 4 weeks of next month on May. So if you want to continue learn about basic lifting engineering, so you can register yourself for the mobile crane stability. We will learn about rough crane and also crawler crane. And I don't remember, the time is the same. The time is the same, is 10 until 12 o'clock. But I will share with you what is the topic. So we will talk about the tipping point. We will talk about the ground bearing stability and also center of gravity for the outrigger and also crawler crane. So we will bring the two topic with outrigger and also with crawler crane. So Thank you so much, everyone. Thank you for Nelson also to bring this topic to all of us. If you have any question related with your capstone, please you ask to Nelson directly, and then also your capstone, you can send it directly to Nelson. Yes, Joseph, do you have any question?
Not a question. It's an appreciation to you, Diane, and Nelson. It's quite a beautiful moment having joined this class. The knowledge transfer is wonderful, and also the delivery is quite sequential. I want to say thank you for organizing this, and also thank Nelson, our teacher, our trainer.
Yeah.
And also I want to thank my colleagues here, Edmond and Mohammed.
Yeah, thank you so much. For the mobile stability, we have only 10 slots. So every class we put the limit. So now we already have I think that there's 7. So we have only left 3 participants. So if you wanna join, you can feel free to join. And rigging designed next month. So every month we keep changing. So next month we don't have basic lifting, and then we don't have mobile crane stability. So we only have SPMT, lifting management system, and rigging design. So we try to change every month, so you're not boring with all advertising that I bring to FDP page or my page. So if we always put the same, so we'll say, oh, why the class is always the same, right? So we try to keep changing, so every topic will different. So thank you so much, everyone. Thank you, Paul. Thank you, Muhammad and Joseph. I will send you the recording. The recording and Google form feedback. And I hope that you can feel the feedback, so we can keep improve our service to all of our participants. And thank you so much, everyone. See you soon for the next class.